Guys, today I am going to cover Unit 4, Section 1 and the behavior of gases with the emphasis on kinetic molecular theory and Boyle's law and Charles' law. Okay, first of all, I would like to cover the behavior of gases, and I want to do a quick review from what we have learned last time. So, to describe the behavior of gases, there are going to be four important factors which affect the behavior of gases. The first one is going to be the volume, and the volume is usually measured in liters. Next one is pressure, and the pressure actually has four different units. They are ATM, which is coming from the atmosphere. This is the pressure we are receiving at the sea level, and we call that 1 ATM for that, which is equivalent to 760 mmHg, which is stands for millimeter of mercury. And this is also equivalent to another unit called torr. This is also equivalent to 101.3 kilopascal. The third factor is temperature, and you're going to be always using the Kelvin scale for the gas laws. So the Kelvin temperature can be found by simply adding 273 to the Celsius. The last one is the number of gas moles, which is represented by the N. Next one is going to be kinetic molecular theory of gases. This is the theory that helps us to understand the behavior of the gases. And this one is made up with the five postulates. And these are the first one is going to be the particles of a matter don't attract nor repel each other. So what it means is that when the particles are in a gas state, particles are not going to attract nor repel each other, so that each gas particle is totally independent. Next one is the gas molecules are in constant random motion, and which causes the collisions with the container walls and pressure. Because gas molecules are in constant random motion, eventually the gas molecules are going to run into the container walls, and which will create the pressure. Third postulate is collisions between gas particles and with container are perfectly elastic. So whenever gas molecules run into each other or against the wall, the collisions is going to be perfectly elastic. Perfectly elastic basically means that energy is conserved even after the collision. So none of the energy after the collision is going to be lost to the environment as a heat or any other energy. The fourth postulate says that the size of the gas particles are so tiny, we're going to assume that the volume is negligible. So basically, it doesn't occupy any volume. The last postulate says the average kinetic energy, the kinetic energy is energy due to the motion, is directly proportional to the Kelvin temperature of a gas. So that means a higher temperature means that there are more kinetic energy. These are the five postulates, or basically an assumption. These are the five assumptions of the kinetic molecular theory, which helps us to understand the behavior of gas particles. I'd like to use this video to explain to you guys further about those gas behaviors. So I'm going to go ahead and pump in the gas into this room. So as you can see, these are the gas particles spreading out randomly and evenly throughout the room. So assume that these little blue balls represent a gas particle, individual gas particle. So first of all, these gas particles are randomly moving around, They're in constant random motion. And whenever the particles run into each other or runs into the wall, right, they are going to be perfectly elastic so that they are going to go back and forth. And also, you should note that when the particles come to each other, they're not going to attract nor repel each other. That each individual gas particle is perfectly individual and independent, so that there's no attraction nor repulsion between each other. Okay, here is another demonstration of elastic versus inelastic collisions. So what does that mean when I say collision between the gas particles are elastic? So let's go ahead and take a look at this demonstration. So these two balls, when they run into each other, right, they were able to conserve their momentum. They just changed their direction. Okay, we're going to assume that none of the energy was lost after the collision. In inelastic collision, here is a demonstration. As the ball runs into another object, right, it completely stopped. That's because all the energy has been transferred into the another object. Energy was not conserved, so therefore the ball did not bounce back. Okay, now based on these kinetic molecular theory, we are going to now tackle many different types of gas laws. So these are the mathematical relationship among the gas variables, and we have a name for each one of those. The first one is going to be called Boyle's law. According to the Boyle's law, the pressure and volume are inversely proportional. Inversely proportional means that as one increases, the other decreases. Here's one important assumption. In order for Boyle's law to work, the temperature and amount of gas must remain constant. Mathematically, we're going to put this as P1 V1 is equal to P2 V2. P stands for the pressure and the V stands for the volume, obviously. Now, the question is, what does that little subscripts 1 and 2 represent? These subscript basically compares two different situations or two different conditions. So when the P and V over here on the left side are tied by the 1 together, we are referring to the pressure and the volume for the first condition. And when you tie the P and V over here together by the subscript number 2, we are basically saying that the pressure and volume for the condition number 2, which is different from condition number 1. So imagine that you have a cylinder containing the gas, which is at the 1.0 liter, and there's exactly 1.0 atm of pressure above that gas. Now, if we increase the pressure, so assume that you are going to be pushing this down further with a stronger pressure at 2.0 atm. Then, according to Boyle's law, the volume has to decrease because increase in pressure means decrease in volume. That's because pressure and volume are inversely proportional. So here is another demonstration of the Boyle's law. So now let's go ahead and do a sample practice problem doing the Boyle's law. The pressure of a gas at 150 milliliter is 1.4 atm. If the volume is increased to 425 milliliter, what will be the new pressure in atm? So for any kind of gas law problems, I strongly suggest that you guys first write down each gas variables and identify which condition it belongs to. So I'm going to simply go ahead and read the question with you one more time and then just write down those given gas variables. Okay, the pressure of gas at 150 milliliter is 1.4 atm. So we are given the pressure from the problem. Pressure is 1.4 atm for the first condition. So that's going to be 1.4 atm. And at 1.4 atm, the volume is given to us 150 milliliter. So I'm going to now call this one V1, volume for the first condition, which is 150 milliliter. If the volume is increased to 425 milliliter, now the volume has changed. Volume has gone from 150 milliliter to the 425 milliliter. So I'm going to label this V2, the second volume or volume for the second condition, which is a 425 milliliter. Now I'm asking what will be the new pressure in ATM. I'm asking for what is the new pressure, to change the pressure, which is now, I'm going to label that P2. And the second pressure is also measured in ATM, and now we need to solve for this one. So based on this given information, we have a P1, V1, V2, P2. You are going to use the Boyle's law. So Boyle's law says that P1, V1 is equal to P2, V2. Now we are solving for the P2, which is over here. So you'll have to rearrange these variables using the literal equation. You have already learned the literal equation, and we are going to use that to rearrange the P2. So P2 is equivalent to P1 V1 divided by V2. In order to isolate the P2, you had to get rid of the V2. So I am going to divide both sides by the V2, and then you get the P1 V1 divided by V2. Now I'm going to go ahead and plug in the numbers. So P1 was found out to be 1.4 atm, and the V1 was 150 milliliter, and the V2 was a 425 milliliter. So I'm going to multiply these two numbers, then divide by this one number, and reporting to the correct number of significant figures. This one is two significant figures, 2 and 3. So the 2 is the least number of sig figs, so I'm going to go ahead and round my answer to the two significant figures, which is 0.49 atm. Here is a Boyle's law practice problem number 2. The volume of gas at 99.0 kilopascal is 3.000 liters. If the pressure is increased to 1.856 atm, what will be the new volume in milliliters? Just like the last problem, I'm going to first go ahead and write down those given variables. So first of all, the volume is given. The first volume that's given to us is 3.000 liters. So I'm going to write it down. And at that volume, we are also given the pressure, which is 99.0 kilopascal. If the pressure is increased to the 1.856 atm, so that's going to be the P2, the new pressure, and I'm going to write that down. What will be the new volume in milliliters, which is V2? So we are now solving for the V2 this time. We are going to be using the Boyle's law again because these given variables can be nicely put into the equation using the Boyle's law. This time we're solving for the V2, so you'll have to isolate the V2, and we're going to get rid of the P2 by dividing P2 on the both sides. So we get V2 is equivalent to P1 V1 over P2. We're going to go ahead and plug in the numbers into the equation. Now, we run into a little problem. We can't just calculate this equation. That's because these two units are not equivalent to each other. P1 is measured in kilopascal, while P2 is measured in atm, and they are not going to cancel each other out. So, since these two units are different and they don't cancel each other out, we'll need to actually first convert one of the unit to the other one using the unit conversion. So I'm going to go ahead and convert one of the pressure unit to the other one. One is measured in kilopascal while the other one is measured in ATM. It does not matter which one you convert into the which one. I'm going to simply go ahead and convert the ATM into kilopascal. I just simply chose this one. So I'm going to go ahead and draw a dimensional analysis to convert the ATM into kilopascal. According to unit conversion we learned the last time, 1 ATM is equivalent to 101.3 kilopascal. Again, this unit conversion factor will be given to you every time. You just need to know how to use that to convert. Once I do this, ATMs are going to cancel each other out and multiply every number on the top divided by every number on the bottom, reporting 4 significant figures from our given number. We get 188.0 kilopascal. Now I'm going to go back to the equation and plug in the new value. You note that now the P2 is going to be converted into 188.0 kilopascal. And once you go ahead and multiply and divide, reporting 3 significant figures, you get the final answer 1.58 liters. However, this is not our final answer. That's because I'm asking for the new volume in milliliters. So I'm going to go ahead and convert 1.58 liters into the milliliter by doing another dimensional analysis for the unit conversion. So we are converting the liters into the milliliters. So this can be done in two different ways, using dimensional analysis or using the metric system. So I'm going to use the dimensional analysis, and then a 1 liter is equal to 1000 milliliter. So once you cancel the liters out, your final answer should be 1580 milliliters. Or if you want to express this number in scientific notation, 1.58 times 10 to the third milliliters. We're going to go ahead and tackle the second gas law that's called Charles' law. According to Charles' law, volume and temperature are directly proportional. So that means when volume increases, the temperature is going to increase as well. This Charles' law also has an important assumption. We assume that pressure and amount of gas stay constant throughout the reaction. So mathematically put together, V1 over T1 is equal to V2 over T2. The V stands for the volume, T stands for the temperature. So here's the demonstration. So we're going to assume that we have a cylinder, again, with a volume, initial volume 0.5 liters, and the temperature is at 200 Kelvin. We're going to assume the pressure is 1 atm, which is going to stay constant after the change. After the change, we are going to heat up the cylinder, and the temperature now becomes 400 Kelvin. So as the temperature increases, the volume is also going to increase. So this is the Charles' law. Therefore, the volume and temperature are directly proportional. Here is a Charles' law practice problem number 1. A gas at 89 Celsius occupies a volume of 0.67 liters. At what Celsius temperature will the volume increase to 1.12 liters? Just like the Boyle's law, I'm going to go ahead and write down my gas variables first. So, first of all, we are given the first temperature, which is 89 Celsius. And then at the 89 Celsius, we get the volume, which is 0.67 liters. And we are going to increase our volume to 1.12 liters. And at this volume, what is going to be the temperature, which is now T2, the new temperature? That's what we're solving for. Based on this given information, T1, V1, V2, T2, we have to use the Charles' law. But for every gas law, you can only use a Kelvin temperature scale. So if you're given the Celsius like this problem, you have to first convert to the Kelvin. So I'm going to go ahead and simply add 273 to the Celsius to get the Kelvin, which is the unit conversion we learned in last time. So 89 plus 273, that's going to be equivalent to 362, reporting the correct number of significant figures. So the Charles law is going to state V1 over T1 is equal to V2 over T2. And we are solving for the T2, so I'm going to rearrange the equation using the literal equation to solve for the T2. So T2 is equivalent to V2 times T1 divided by V1. I'm going to plug in my numbers, 1.12 liters times 362 Kelvin divided by 0.67 liters. Now reporting to the two significant figures, this is going to be equivalent to 610 Kelvin. But the question is asking for the Celsius temperature, so we're going to go convert Kelvin back into the Celsius. This one, you're going to have to do the backward, where you have to subtract 273. But remember for the significant figure rules for the subtraction. For the subtraction and addition, you have to round your answer to the least accurate measurement. And 273 is a conversion factor itself, so it's not going to affect your significant figures. Only the given number, which is 610 Kelvin, is going to determine the significant figures. 610 has two significant figures, 6 and 1. And this number is measured only accurate to the nearest tens because of the ones digit is not significant figure. So your answer has to be only reported to the nearest tens, which is therefore 330 Celsius. Charles law practice problem number 2. What is the volume in liter of the air in a balloon that occupies 0.620 liter at 25 Celsius if the temperature is lowered to 0.00 Celsius? Again, I'm going to go ahead and write down all my variables. The first temperature happens to be 25 Celsius. And at that temperature, the volume is 0.620 liters. And we are going to lower the temperature all the way down to the 0.00 Celsius. And we want to find out the new volume, V2, at this new temperature. We are going to use the Charles law because these given variables will align perfectly to the Charles law. But again, we're going to have to first convert any Celsius into the Kelvin. So we are going to add 273 to make it into the Kelvin, and this one too. Note that this first number, the 0.00 Celsius over here, has three significant figures. And these significant figures, this one is measured all the way down to the 100th. That's why the Kelvin is going to be measured to the nearest 100th. So the Charles law, V1 over T1 is equal to V2 over T2, and we are solving for the V2 this time. So we are going to use the literal equation to rearrange the formula to solve for the V2. V2 is equal to V1 times T2 divided by T1. We are going to plug in the numbers into the formula, and then we are going to calculate this using the least significant figure for the multiplication and division, which is going to be 0.568 liters.